Okay, guys. So again, please, I appreciate your questions have always been good. And if you have any, please ask them. All right. So let's go through here. I'm going to talk about just a couple of more reactions, and then I'm going to practice some synthesis with you in the time we have remaining. So this next couple of slides shows you how you can prepare alkynes, from alkenes, all right? Let me move this out. So how do you prepare an alkyne from an alkene? Well, the way to do it is from a dihalide. And you can either have a geminal dihalide. Geminal means the two halogens are on the same carbon. Or you can have what's called a vicinal dihalide. A vicinal means the two groups are on adjacent carbons. Vicinal adjacent carbons, geminal, the same carbon. So the way it works, you have a strong base added. I'll show you what base is typically used in a minute. And you get two consecutive E2 reactions. So I'll show you, it's shown here. So the base takes off a beta hydrogen. The electrons go in here to form a double bond, and the leaving group is kicked out. That generates an alkene. So you've removed H and Br, and you went from a single bond to a double bond in an E2 reaction. You still have one of the two bromines remaining. And then the strong base can do a second E2 reaction, right? So the base takes off the other beta hydrogen. The electrons go in here to form a triple bond, and the leaving group's kicked off, right? So it's two consecutive E2 reactions, right? So you see okay, so that's how it works. And you can do the same thing with a vicinal dihalide and strong base. So let me show you a little more about this. So here's an example I want to show you. So we're starting with 1-butene, an alkene, and I'm going to end up, I left out some, this isn't right. I have 4 carbons here. So we're going to end up with 4 carbons. And then when we add water, I'll explain each step here. Okay. So the first step, converting an alkene. So we have a 4-carbon alkene, butene, and we're going to convert it to a 4-carbon alkyne, butyne. Okay, that's 4-carbon alkyne from a 4-carbon alkene. So this is how you do it every time. The first step, you brominate. So you brominate the alkene, right? And then you add this sodium amide excess. You usually have an excess, like 3 equivalents. So this is how it works. All right, it doesn't matter. We'll take that sodium amide. The amide ion is NH2, AM amide. The amide ion, NH2 minus, is a very strong base. You take off the first one. These electrons go in here, kick out the leaving group. That gives you this, right? So you lose Br minus, right? And NH2 minus picks up the H and becomes ammonia. Okay, you get that. Okay. So this Br is still there. We didn't kick that one out yet. And then you still have a hydrogen here. This is the first E2 reaction. And then you have 3 equivalents of NH2 minus. I'll explain what the third one's for. So the second equivalent now takes off this hydrogen. These electrons go in here, kicks out the leaving group, and that gives you that's 4-carbon alkyne, right? Butyne. Okay. And Br minus gets kicked out. And NH2 minus picks up another hydrogen and gets kicked out of ammonia, right? Now there's a hydrogen here, right? 4 bonds to that carbon. So now there's a third equivalent of NH2 minus. I'll explain why that's necessary. So one equivalent, two equivalents, three equivalents. That takes off this hydrogen, acid-base reaction. So you get the conjugate base. Okay, ammonia is kicked off. And the reason that's done is that drives the reaction to completion. Otherwise, it's kind of an equilibrium process between the alkene and the alkyne. You don't get apparently a good yield of alkyne, but by having that third equivalent of base, you remove this hydrogen. NH2 minus is a sufficiently strong base to take a hydrogen off of the alkyne. You form this anion, and then that drives the reaction to completion. And then in the third step, water is added. So this is step one, as I said, step two, and then you add water, and then the water puts the hydrogen back on, okay? And that's it. So you've converted the 4-carbon alkene into a 4-carbon alkyne. That's the whole mechanism. In terms of synthetically, you just bromine, step one, excess NaNH2, step two, you add water for the protonation, step three, okay? And I'll show you other examples of that later. Okay, so here's an example. So we would, I left out the bromination step, right? So we start with the dibromide, excess sodium amide. This NH3 is the solvent that the amide is in. That forms a triple bond, and then you add the water, okay? That's how it's done. You can do it. Okay. Okay, so we'll come back to using that in a synthesis later in the period. Okay. So I want to go over, this is the last reaction in this chapter, and it's an important one in organic synthesis because it lets a person build a longer carbon chain from a smaller one, right? So if you're going to do organic synthesis and you want to make more complex molecules from less complex molecules, you have to have methods of building or extending a carbon chain. And the reaction I'm going to talk about does that. Okay, the first thing I want to point out is that a terminal alkyne, that's an alkyne where the triple bond's at the end of the chain, so there's a hydrogen attached. This is an sp carbon, and sp carbons, they're weak acids, but they're much more acidic than hydrogens on double bonds, or much even more acidic than hydrogens on single bonded carbons. And so very strong bases like this NH2 minus anion, the amide ion, can remove the hydrogen in an acid-base reaction and form the conjugate base of the alkyne. And that's called an alkynide ion, okay? So let me show you the energy changes here. So this shows you we're starting with acetylene, an alkyne with hydrogens on the triple bonded carbons. We have the NH2 minus, so you get the acid-base reaction. NH2 minus takes off the hydrogen, forms ammonia, and the conjugate base of the alkyne, the alkynide ion, right? So this is an acid-base reaction. The pKa of the alkyne hydrogen is 25. You can look that up in the table. That's the acid on the left side of the equation, and the acid on the right side of the equation is ammonia. That has a pK of 38. So remember, the equilibrium favors the side with the weaker acid, right? The stronger acid ends up giving up its H plus and ending up as its conjugate base. So this is a favorable reaction thermodynamically. This goes to completion, all right? You can remove a hydrogen on a triple bonded carbon with sodium amide because the thermodynamics are favorable. Now, if you try sodium hydroxide, you see it's not favorable. Hydroxide is not a strong enough base because here you see on the left side, the acid is the acetylene, the pK is 25. The acid on the right side is water, pK is 15. So you see water is a stronger acid than acetylene and has a lower pKa. So the equilibrium, right, favors the side with the weaker acid. And the weaker acid here is the acetylene. So this reaction here would have an equilibrium constant much less than 1. So if you want to generate the alkynide ion, you can't do it with hydroxide. It's not a strong enough base. You have to use the sodium amide, right? That's really the lesson there. Okay, so now I'll show you how you can use alkynide ions in synthesis, how you can extend the carbon-carbon chain. So these alkynide ions are very good nucleophiles. They're strong bases too. They're very strong bases and they're very strong nucleophiles. And so you can carry out SN2 reactions on alkyl halides. But because they're strong bases, you're limited to methyl or primary halides, right? You can't, you see, so you can displace a halide ion as long as the halide is primary or methyl. What happens if the halide is secondary or tertiary? Well, remember we've talked about this. It's in the tables I posted and in the textbook. With strong bases, secondary and tertiary halides don't undergo substitution. They undergo elimination to form alkenes via an E2 reaction. And that's shown here. So if you generate an alkynide ion, try to generate an alkynide ion, and you react it with a secondary halide, for example, you get E2 elimination. You get the alkene and not the substitution product. So because of that, this is a great way to extend the chain, but the limitation is the halide you use has to be methyl or primary, okay? So let me show you how you do it now. So this is how you do it. We start off with acetylene, and you do this, you want to add an ethyl group. You first deprotonate the alkyne with sodium amide. So the amide ion, right, we saw can take off the hydrogen, form the alkynide ion, right? And then in the second step, you add whatever alkyl halide you want to, whatever alkyl group you want to add. Here we have ethyl iodide, right? CH3, CH2 iodide. That's primary, so we carry out an SN2 reaction, and we introduce the ethyl group. So we've gone from a 2-carbon chain now to a 4-carbon chain, right? And now, if you start with acetylene, well, you have another hydrogen that's acidic, so you can do this a second time. You can take the amide again, take the amide ion again, deprotonate that alkyne, generate the alkynide ion from that one, and now we've chosen to add a methyl group, but we can add propyl groups, ethyl groups, and so we add methyl iodide now, MEI. You get SN2 reaction, you add the ethyl group. So in these two consecutive reactions, we've gone from a 2-carbon chain to a 5-carbon chain, okay? And now what you can do is you can start modifying, you can react the triple bond, you can reduce it to a double bond, and we saw many things you can do to a double bond to introduce new functional groups. We saw you can introduce new functional groups directly to the triple bond as well, okay? So I want to show you some of that. So that's how you build it. Deprotonate the alkyne, create that nucleophile, carry out SN2 substitution on a methyl or a primary halide, and And that's how you get going. Right? So let's see, let's try to synthesize this molecule here. And we want to start from acetylene, or ethine is the systematic name. Okay, we're going to do both of these. So we got acetylene, and this is 1, 2, 3, 4, 5, 6, 7. So we have one heptine. So I am going to show that on the next slide. All right. So, oops. So here we go. We're starting with acetylene. All right. And we want to make one heptine. So it's 1, 2, 3, 4, 5, 6, 7. All right. That's the synthesis we have. So here's how you got to think about this. You're starting with a 2-carbon chain, you end up with a 7-carbon chain. So you have to use a reaction to extend the length of the chain. Well, at this point in your study of organic chemistry, you only know one way to do that, right? Through the alkynide ion synthesis that I just showed you, right? So we're going to have to do the alkynide ion synthesis. So the first step is what? You take sodium amide and you generate the alkynide ion, right? It's a sodium salt, right? But I won't show the sodium ion, right? Just the active species. So you form the nucleophile, and now, well, look, we want to add this 5-carbon chain. So we can do that. We can just add a 5-carbon chain. Look, Br 1, 2, 3, 4, 5, right? Excuse me. So this is a primary carbon, right here. So that's an SN2 reaction. It's really good on primary substrate. And so now we've added the 5-carbon chain to the 2-carbon acetylene. 1, here's the chain, 2, 3, 4, 5. And that's the product molecule that we wanted. 1 heptine. Same thing. I just drew it back the other way. Okay. So that's how you do it. So let me show you another one. And let me take a look at what we had on the previous slide, because I don't remember. So let's do this one here. So we want to go from acetylene to this compound. 1, 2, 3. It's a 5-carbon chain here with the triple bond attached to a benzene ring. So let me see if I can remember to draw that. So we have a benzene ring. I'm going to just, pH stands for the benzene ring. And then we had 5-carbon chain, if I remember, 3, 4, 5. I think that was the molecule. And we want to make that from acetylene, okay? That's the problem. Remember, benzene, pH is a phenyl group, and that is a shorthand for the benzene ring, right? pH is phenyl, right? Okay, so how do we do that? Well, the same kind of thinking. You started with a 2-carbon chain, and started with a 2-carbon chain, and you ended up with, well, a lot more carbons. So we have to use the alkynide ion synthesis, right? So let's do it. We have to generate the alkynide ion. We use the sodium amide, right? There's the alkynide ion. The NH2 picks up the H and forms ammonia, but you don't have to show that. Just show the product. And now, look, we added an ethyl group to one side of the triple bond. And then on the other side of the triple bond, we added that benzene CH2 group, which, by the way, is called a benzyl group. So you have to add 2 groups. And remember, we have 2 acidic hydrogens, so we can add alkyl groups to both sides. It doesn't matter Absolutely doesn't matter which one you do first. So I'm going to add the ethyl first. Let's take ethyl bromide. Right? So you'll do the SN2 reaction that we studied in chapter 7, add the ethyl group. Okay, so we've taken care of that side of the molecule. And now we want to add a benzyl group. So we have a second acidic hydrogen, so we can do another, remove that second acidic hydrogen. And now we add a benzyl group. So we just take this benzyl, I don't know, let's take chloride just to mix it up, okay? So notice this is a primary carbon. That carbon only has one carbon bond to it, the carbon of the benzene. So that's primary, it's good for SN2, right? So here we go. We go attack the alpha carbon, kick out the leaving group. And now we have the benzyl group attached to the triple bond, and we already had attached the ethyl group. So that's the molecule, okay? So two successive alkylations, okay? Adding alkyl groups, okay? Okay, any questions about that, all right? All right, so now I would like to take it one step further with the synthesis. So I'm gonna erase this. Go to the next slide. So now I want to take now we reviewed how you can extend or build the carbon chain using the alkynide ions. And now I want to look at, okay, we do that, now we want to introduce different functional groups. So how do we do that? And now in all these cases, we're going to start with ethine, acetylene. Okay, so let's do the first one, 2-bromopropane. How do you make 2-bromopropane from acetylene? Okay, let's look at that one. And I'll go through all these syntheses and it'll give us some practice. With some of the reactions we studied before. So we want to start with acetylene. Started with acetylene. And we want to make 2-bromopropane, right? That's the first problem. Okay, so how do we do that? Okay, so again, first thing to look at, we got a 2-carbon chain, we went to a 3-carbon chain. So we have to use the alkynide ion synthesis to add a carbon, right? Okay, so we can, I've been emphasizing working backwards, but maybe now we can try working forward here. So the first thing we do is NaNH2. So we form the alkynide ion, good? Okay, so now we just want to add 1 carbon. We went from a 2-carbon to 3-carbon. And that's kind of easy to do. I don't know if I mentioned this to you, you always should use methyl iodide. Methyl iodide is a liquid, whereas methyl bromide and methyl chloride are gases. And it's much easier to handle liquids. You can work with gases, but it's much easier to work with liquids. So you take methyl iodide and you carry out an SN2. Right, so now you add the methyl group. Now we have the 3-carbon chain propyne. And we want to convert that to this bromide. So we know we can add Br to an alkene, right? Our carbon-carbon addition to an alkene. So how about if we reduce this to an alkene with, remember the catalyst, you can use Lindlar's catalyst. That will give us an alkene. Okay. So hydrogen with Lindlar's is one way of converting an alkyne to an alkene. Remember, these reactions are your toolbox that you use in synthesis. And now we can just convert the alkene to the bromide by adding HBr. It's Markovnikov addition of HBr, right? So that's a one step. Form the alkynide, alkylate, add the methyl group, reduce the triple bond to a double bond with hydrogen and Lindlar's, and then the fourth step, you introduce the bromine functional group, okay? So that's a synthesis there, okay? So we'll keep moving. If there's no questions, I'm gonna clear this. I wanna work a few more of these problems in the remaining time that we have. So let me go back. So let's do this one down here. Let's take, starting from acetylene, let's make 1 butanol. Okay, so let's try to do that. So we're starting with acetylene. And we're going to make 1 butanol. That's the object here. Right? How the heck you do that? Okay, so a couple of things you can initially consider is one, we've gone from a 2-carbon chain to a 4-carbon chain, so we have to do the alkynide ion synthesis, right? And then we know ways of introducing OH groups into alkenes, right? We know how to make alcohols from alkenes. So kind of a strategy here, we extend the chain with the alkynide through the alkynide ion, make it 4 carbons. Then we can convert the triple bond to a double bond, right? And then we can add the alcohol. There's one other way you can do it, which I'll show you. Sometimes there are more than one way to do these problems. So we're going to form the alkynide. All right, that's the same. And now we started with 2 carbons in the alkynide. We want to add 2 more. So let's take the ethyl bromide, let's say. We did that before. Carry out the SN2 reaction. You don't have to show these arrows, by the way. When you're doing synthesis, all you have to do is show the reactants, substrate, and the reagents, and then the products. You know, I'm just showing arrows to emphasize what's going on. And then, so that extends that to 2 more carbons, right? Now, we don't know any way to directly introduce an OH to a triple bond. So what we have to do is we have to reduce it again to an alkene. So we can use H2 and Lindlar's again. Remember, if you don't use Lindlar's, if you just use hydrogen and platinum or hydrogen and palladium, you're going to reduce it down to the alkane, the single bond. So you want to stop it at the alkene stage, you have to use the Lindlar's catalyst. That reduces it to the alkene. Okay. And now, okay, we can do this. We can get the final product, form the 1 butanol. So you see that requires addition of OH to the less substituted carbon, right? It requires the addition of OH to the carbon with the greater number of hydrogens. So we know how to do that. Anti-Markovnikov addition of water, BH3, borane in the THF solvent, followed by hydrogen peroxide in basic solution. All right, that does it. So that's your synthesis. 1 step, form the alkynide ion. 2 steps, you form the extended chain, 4 carbons. 3 steps, you convert the triple bond to a double bond. And the 4th step is you do the anti-Markovnikov addition of water to give you the product that you wanted to make. Okay? Any questions? Okay, no question? You guys are good? All right, I take that as you guys are good. So I want more practice. I want to practice as much as we can in the remaining time.
When we're doing these, would you recommend that we write out the full chain, or can we just abbreviate it? Like,
Yeah, you can abbreviate. It's okay to abbreviate with the bond line drawings. I'm just doing it here with the full chain, just to be as clear as I possibly can be, okay? But it's perfectly okay to use bond line structures. Yeah, thank you. Okay, let me do one more here, and then there's one other type of problem I want to do. So let's do this. All right. Okay. Let's try that one. So we are trying to go from affine to that ketone, right? So we clearly have to build a chain from 2 to 4. We know how to do that now. But the other reaction I want to remind you of is this reaction. That if you have a terminal alkyne, all right, this is, and you take you need the mercury salt here. You got this mercury salt as a catalyst. Then you have sulfuric acid in water. Okay? That's the equivalent, of course, of H3O+. So what you get here is you get addition. Remember, you get Markovnikov addition of water. Right? Remember that sulfuric acid and water to an alkene gives you an alcohol. Sulfuric acid to water to an alkyne gives you, remember what these are called? Enols, right? And when I say went from a triple to a double bond, of course. And what we discovered or learned is that these enols are unstable and they isomerize to in this case, a methyl ketone, right? Okay, so you summarize to a methyl ketone. So the final product of the addition, acid catalyzed addition of water to an alkyne is not an alcohol, it's and with these reagents, you get a ketone, all right? So you see the final product here. That final product here, let me redraw it. Now I'm going to work backwards. I use this arrow to remind myself I'm working backwards. That ketone can be made from this alkyne, this terminal alkyne. Okay, you can take this terminal alkyne, react it with the sulfuric acid water with the mercury catalyst, and that will give you that ketone. All right. So the target is that we have to build that, and now we know how to do that, right? I think now you can probably do it. I hope pretty easily. You start with the. I'll do it one more time. I don't know why it's doing that. Okay, you start with the. Starting material, right? Sodium amide. Let's combine them into 2 steps now. And you can do that. Sodium amide, and we want to add 2 carbons in ethyl group, right? So we want to add, let's take ethyl bromide, all right? Form the alkynide ion and do the SN2 reaction. And so you get now, you get the 4 carbon chain, which is what you want, right? And now we learned, and you can do this stepwise if you want. If it's easier for you, some people find it's easier to just do it stepwise. You end up with the methyl ketone. That's it. You can just draw that. You don't have to draw the intermediates when you're doing synthesis. You just write the substrates, reactants, and product. But if it helps you think about the problem, then you can say, oh, wait, we're adding water to a triple bond. We're going to get an enol, right? We're going to get an enol intermediate, and there goes that isomerization to the ketone. Okay, so that's how you do that. Okay, that makes sense, guys. I hope so. Okay. All right. Any questions? Any questions? Okay. I take that as absolute complete understanding. Okay, let me go on to the next one. One more, just a little more. What I want to do here is give you a slightly different type of synthesis problem. And so I can remind you of another cup reaction that's relevant, important. So in the first one here, which we'll do, is we're starting with an alkene, 1-butene, and we're making an aldehyde. Okay, so let me write that on the next slide. 1-butene to that 4-carbon aldehyde. So here it is. We're starting with 1-butene, and we want to make 2, 3, 4. We want to make a 4-carbon aldehyde, right? So, yeah, I can't emphasize enough the importance, and I think you see it, of learning reactions, right? So you can use them in these kinds of problems. So that's where you need the drilling, the index cards, however you review your reaction summary sheets. I'll put up a summary sheet too. I did that for the reactions in chapter 8. I have a summary sheet of all the reactions as well in chapter 9. And at the end of the chapter, the book also has a summary of all the reactions. It's all there at the end of the chapter. So what I want to remind you of here is to make an aldehyde, the way to do it is you have a 4-carbon aldehyde here. You have to have like a 4-carbon. You can make that this is the only way we know of making them. You start with this 4-carbon alkyne, and then you want to do this reaction. You can't do the aqueous acid one. You can't do the aqueous acid. That gives you a methyl ketone, right? We saw that on the previous slide. Aqueous acid with the mercury salt gives you a methyl ketone. But now you basically want to add the water anti-Markovnikov. You want to add the water anti-Markovnikov. Okay, if you add the water anti-Markovnikov, where the OH goes to the less substituted carbon, then you know when it undergoes the isomerization, then you'll end up with the aldehyde, okay? So how do you do that? Well, normally we add water to a double bond with BH3, but remember BH3 gives you a mixture, so they have to use these 9-BBN, that's a sterically modified, or just this, you can write it in this way. This is in the THF solvent, all of these. You got these modified BH3 reagents that prevent these side reactions, and then you do the normal H2O2 sodium hydroxide. That gives you the anti-Markovnikov addition of water, and then this isomerizes to the aldehyde, okay? So the target really, once you recognize that, is to build that 4-carbon triple bond. And this allows me to review that reaction we started the period with, is converting alkenes to alkynes. And the way to do that, remember, is you brominate. First you brominate. I'll show you the reactions again. Then you use excess sodium amide. And then the final step, you add water. And that converts that converts that 4-carbon alkene into a 4-carbon alkyne. And the way that works is this. I'll show you again just as a review. Whoa, what happened there? I don't know what the hell happened there. Oops. I don't know. Okay, you guys still there? Okay. So sorry about that. I have no idea what I did. So we started with the four, if you remember, we started with the 4-carbon alkene and we converted to the alkyne. So the first step I said was bromination. I'm going to wrap it up here in just 1 minute. You can bear with me. We brominate. Then you use excess sodium amide. That does 2 consecutive E2 reactions, right? You eliminate HBr once, that gives you an alkene. You eliminate HBr again, that gives you an alkyne. The excess amide deprotonates the alkyne to give you the alkynide ion. That drives the reaction to completion. And then you add water to protonate the alkyne, right? Oops. That gives you the final alkyne we want. And then we saw we can form the aldehyde from that on the previous slide, okay? So